Yeah, so it's, sorry. Right. So this is a semi-outsider's review of gravitational wave FRB connection. My engagement with the FRB community was my study of the persistent radio counterpart, which the first one which Aravind presented before he took over with the GMRT, a study that we presented, we did with my collaborators, Rako Vink and Ishwar Chandra. But I have a strong interest in multi-messenger astronomy, which is mainly due to my association of gamma-ray burst physics. So this is in this background that why I said it is a semi-outsider, because I haven't really gone into FRB studies with working out FRB connection with gravitational waves, but until now. So, but maybe this is a beginning. Thanks to Jayanta for asking me to give this talk. So, what is multi-messenger astronomy? We have so far known at least four messengers through using which the universe speaks to us: electromagnetic radiation, cosmic rays, neutrinos, and gravitational waves. In this order, to a good extent. So these are at least the four known messengers that we have. And gravitational waves officially became the messenger in 2015 when the first gravitational wave source was observed with the advanced LIGO-Virgo detectors, which was the merger of two black holes of 36 and 29 solar masses at more than 400 megaparsec from us. This signal we see here is a sketch of the numerical relativity signal and reconstructed template of the merger of two black holes. The black holes initially show an inspiraling phase. They come closer and merge and ring the phase of ring down after the merger. All these all the phases are shown here, where we can see that the time and the frequency, as time goes on, the frequency is going up, and in another way of presenting this, one can also see the amplitude of the signal will go up and will peak around the merger. So both the frequency, which is a representation, which sort of connected to the orbital frequency of the components, both the frequency and the amplitude will intuitively, one can see that it will go up and reach the peak towards the merger. So since then, the LIGO-Virgo-Kagra interferometer network has detected several binary black holes, binary neutron stars, and neutron star black hole mergers. These are all bursting transient events. Here is a very older version of the LIGO-Virgo-Kagra catalog of gravitational wave transient events. What I just now mentioned, that the amplitude going up can be seen with this color scheme here. And on the frequency, this y-axis is the frequency and the x-axis is the time. Then you can see that the transient signal, as it starts coming from here, peaks here as the merger occurs. So these are different type of, this is the merging two neutron stars, and there are also merging black holes. LVK has also seen merging neutron stars and black holes. This is also another very famous picture, a sketch of the masses in the stellar graveyard, what kind of compact binary coalescence has LVK has so far seen. This is the most recent one, so you can basically see how the masses are all, what sort of events are merged. So for example, you can see two masses merging and becoming a third mass. So this entire picture is something which you can go and check later. We will not go much into this. What about other type of sources? LVK has so far only seen this merging, coalescing compact binaries or CBCs. This depends. Why don't? The fact that we are only seeing these type of sources is because not because other sources cannot emit gravitational waves, but because because we have this ground-based interferometer network, and the gravitational wave detectors work by looking at the changes in the interferometer fringes as when the space-time is when a gravitational wave passes through the interferometers. So it depends on the length of the arms. So of course, when in future, so this is just an animation of how the interferometers work, and this as the gravitational wave passes through. So definitely the fringe changes in the fringe of the interferometer, which is later decoded as the gravitational wave signal. What sort of frequencies you can probe will depend on the antenna length. So this is why in future, when the laser interferometer space antenna, where the interferometer arms can be much, much longer because the interferometer will be in the space, we can really see other kind of sources, say, for example, white dwarf binaries, coalescing supermassive black holes, neutron star stellar mass black hole. Many of these probably, one doesn't know whether these sort of sources may have something to do with FRBs. That's why I brought it here. So the summary is that right now we see CBCs in gravitational wave detectors, but in future we can also see other sort of sources. Well, so this was all about just the gravitational wave detection. What about multi-messenger astronomy? Multi-messenger astronomy is when we are able to see two messengers. Here in this talk, I'm focusing on gravitational wave and electromagnetic radiation. The two messengers from the same phenomena, which will improve our understanding of the physical process in several dimensions, because the two messengers will be coming from two different parts of the source. So they'll be complementary. They'll actually be arising from different physical processes, one from the gravitational interaction, the other from the electromagnetic interaction. So here is the first and only one in multi-messenger astronomy signal in GWEM that we are so far aware of, which is the merger of two neutron stars. This is the chirp signal, the similar thing that I had shown earlier, where the frequency and time goes up at the time of the merger. And this is what the LIGO-Virgo LIGO-Virgo detectors have seen. And what made this event, of course, interesting is, of course, the electromagnetic signal temporally and spatially associated with this in the form of a burst of gamma rays. Which we can see that the time of merger, soon after that, around 1.7 seconds later, there is a burst of gamma rays detected by the Fermi Gamma Ray Space Observatory and the Integral Gamma Ray Observatory. This is also spatially coincident, which confirmed a well-known hypothesis that this class of burst of gamma rays called gamma ray bursts are associated with merging neutron stars. And not only that, this event was much more important. It was one of the most significant event in the entire history of recent astronomy, that this source was also seen in other wavelengths like radio, X-ray, optical, and optical near IR, UV, etc. These are two different type of sources. One, following the binary neutron star merger, there is a jet that is producing the gamma rays, which further produces X-ray and radio emission. And there is also a source called kilonova, which produces most of this optical IR UV emission. So you have actually two electromagnetic sources. One is the gamma ray burst, and the other is actually three, because one is the gamma ray burst, the other is the afterglow, which is seen in X-ray and radio. And the third one is the kilonova, associated with one type of gravitational wave sources. This is a golden multi-messenger astronomy scenario. Unfortunately, we have just this one. And this is where our work also comes in, because we also joined in this. We observed this the source with GMRT, and there are several other teams which observe the same source. So I'm just only writing our collaboration's name. So of course, this has led to a lot of deep understanding in the in our idea of both gamma ray burst and binary neutron star mergers. The kilonova, which I mentioned, was the first time being detected. So now going ahead to, is it possible to have such groundbreaking discovery with FRBs? Can we see fast radio bursts associated with gravitational wave signals or vice versa? It's a very difficult question at the moment. So there will be a session. I mean, I think I understand that there will be two sessions on Thursday and Friday about FRB sources. What kind of sources can produce FRB signals? So as I said, this is just a very, very brief overview of this. I am based mostly by this excellent review article by Bing Zhang in 2024. So let's say even if we consider independent of whether there are all the repeaters are really all the known repeaters are really known repeaters, or are they repeating FRBs with a very long wait time? We can definitely, there are two types of sources that have been discussed in the FRB literature. The ones that can power, the sources that does not end with the production of an FRB, which is required for repeating FRBs, and the other kind which is the result of a cataclysmic event. In both cases, the magnetars are a favorite candidate. So most of these models involve magnetars tapping their magnetic energy reservoir and producing FRBs. There are models which are based on pulsars, giant pulses, or interacting neutron star systems where the spin or gravitational energy is being used up to produce the radio burst. In the cataclysmic models, the most favorite model is of combat binary coalescence. There are also other models called blitzers, where there is a neutron star ejecting its magnetosphere when it implodes as a result of perhaps a merger, or perhaps its rotational angular momentum can no longer support it. So here are some small numbers of these models. Here is, so what sort of scenario is there? The BNS mergers normally produce, as I mentioned earlier, for 1708, 17 also. It's a very messy environment with a tidal ejecta, that is neutron-rich tidal ejecta produced from the merger, because both the neutron stars gets ripped apart, and also possibly eject. So there is, of course, a question that even if there is an FRB signal that gets produced, is it possible to escape this messy environment? Another possibility is that the signal, FRB signal, is produced before or after the merger. So such models are one of which is a unipolar inductor model, where the weakly magnetized neutron star has two neutron stars in spiral and well before their merging phase, the weakly magnetized neutron star will be going through the crossing the stronger magnetic field of the other neutron star. This is the sort of model which was proposed for Jupiter and its moons system. And the calculations sort of show that it can produce a luminosity of something like 10⁴ per second for this sort of magnetic field and the separation between the two stars. We can actually see that this is very close to the merger with a separation of 30 kilometers. Another kind of physical model is the classical theory of radiation, that the accelerated charges radiate. So you have a charged CBC companion, which is a neutron star in the combat binary, which is having a charge. Global charge. As it accelerates, as it as it orbits around its companion in the common center of mass, it accelerates, and dipole radiation and both electric and magnetic radiation can be produced. And this sort of calculations show something like 10⁴ ergs per second or so. Both are the sort of energies that we see in FRBs. The before merger scenario has the sort as I mentioned earlier, if the FRB emission can come before the merger, then there are also models where magnetic reconnection in the interacting magnetosphere that produces repeating FRBs. One good thing is the matching with the luminosity and also the potential for LISA detection, because LISA is can possibly detect in spiraling combat objects before they merge well before decades or centuries before the merger itself. What about the after merger? The post-merger, if there are two neutron stars, you can either form a long-lived supramassive neutron star, or a stable neutron star, or a black hole, depending on the equation of state of the neutron star and the mass of the components. If you have a supramassive neutron star, as I mentioned earlier in the Blitzar models, it can eject the magnetosphere when it collapses to black hole after living for some point of time, and this could lead to an FRB-like event. If there is a stable neutron star, perhaps if the magnetic field is high, probably repeating FRBs could be produced. In case of neutron star black hole mergers, there are two types of course, the end products will be a black hole, so a repeating FRB is impossible from such a scenario. But a post-merger repeating FRB system is impossible. But NSBH mergers are two different types. In one type, depending on the mass ratio and the spin of the black hole, it could either disrupt the neutron star when there is the material that is around the system, or it could just swallow the neutron star. Depending on these cases, there are different suggestions or proposals. I will not go more into details of these. So this is just a summary of everything that I mentioned, but because there isn't much time in hand, I'll just go ahead in the searches that people have conducted so far. There have been searches of gravitational wave signals in O3A, several associated with the chime FRBs, and they haven't, of course, found any significant evidence. However, having no significant evidence for association does not mean that you can exclude GW association. So using the volumetric rates of BBH and NSBH and BNS and FRBs, the conclusion that the paper has arrived at is that at most 15% of FRBs could possibly associated with with BNS mergers and 1% with NSBH. This conclusion is based on this huge difference that we can see between the volumetric rates of FRBs and NSBH and BNS systems. There was a GEO600 search for the galactic SGR FRB it occurred at a time when LVK was not operational. It was temporarily halted. At that point, there was a search by the GEO600 instrument, but not anything was discovered. There was also a putative association of an FRB and a BNS merger, which was this, of GW 190425 and FRB 2019-0425A, which is somewhat this FRB, which was detected in chime in 400 to 800 megahertz band, 2.5 hours after the BNS merger. The DM distance was consistent with the GW distance posterior. This is the FRB, and this colored map is the GW localization posterior. So there was also a hint of a gamma ray excess by the integral emission. However, we have Mohit Bharadwaj's work, which argues that there is an unlikely possibility of an association, which depends on the viewing angle and the present need of having a clean space for the FRB signals to go on. However, this is one important event. And the second one and last one is this, a low-far coherent source associated with a gamma ray burst, the kind of gamma ray burst that is expected to be produced by the merger of two neutron star or a neutron star black hole system. This again, so such coherent radio pulses are proposed, hypothesis to be associated with compact binary coalescence. So LOFAR seem to have seen something like this, but it is also a sort of weak association. Nothing conclusive could be said at this point of time. But if it is truly associated, it is a case of post-merger FRB emission, because the coherent radio emission is around 5.6, about 76 minutes after the short GRB. But this was a very low significance event as far as I know, so not much of the radio signal properties are clear to me. So with this, I'm stopping here. And
thank you, Rashmi. We have time for one or two questions, quick questions.
Thank you for the talk. I have a very naive question. So we all know that FRB's positional uncertainty is very small compared to the positional uncertainty of a GW event. So how can one overcome these kind of difficulties to figure out any association between FRBs and GW event?
So what was the beginning? I missed the word.
So the positional uncertainty, the error in RA and DEC.
Okay. Yeah. So one... see, the problem more with GW FRB localization uncertainty, gamma ray bursts are reasonably better localized thanks to, so for example, in the LOFAR case also, the localization of the, I didn't explain that, the localization of the gamma ray burst signal was much better. Gravitational wave and FRB association does suffer from this problem, that both if it is I understand that the chime localization has improved drastically now, but gravitational wave localization capabilities are still not very high unless LIGO India probably comes up and improves this. So definitely there is an association issue. And maybe an escape from all this is probably another kind of electromagnetic signal, maybe in X-rays or radio waves, which can be a more like for example in 1708-17, the longer lasting radio emission could actually be used to pinpoint the location or optical signal. If we have that, that will be better.
Any other short, quick questions? Yeah, one.
So generally the uncertainty in when you calculate the rates for the say the mergers, that is pretty high. So if you just factor that in, will it be consistent with the FRB rates, or how will it change?
Did you mean this number? This number? Is this what you meant?
Yeah, you can see here also the rates are very have a wide range.
Yeah, but still the FRB rate, this is the rate of volumetric rate of FRBs with luminosity larger than 10⁻42 per second. That is still actually much larger, right? In comparison with the BNS rates are actually in fact gone down. I don't remember which number this is from. I think GWTC3. TC4 actually we haven't had much BNS mergers, so we have actually gone down. So I think it's actually going in the other way around. Maybe the only option is to say that the even more luminous FRBs are probably only associated with. I mean, that's what I'm saying.
Okay. Thanks.
Jayanta.
So Resmi, when you like in this slide, when you talk about 15% of the FRB could have double neutron star, the binary neutron star merger association. So is this considering the post-merger scenario, or is it pre-merger, or is combined both?
Okay, so this is just the search of GW signals, 3 associated with chime FRBs. They were just checking for temporal and spatial coincidence of a GW signal with chime at that time. I think chime has a much larger error region. So mainly maybe all they were checking for a temporal coincidence to within whatever error region that you can have. And they found no association, which does not rule out so then all that they can say is the maximum is this, that. Yeah, so it was just, probably it is not, you cannot really say, for that I need to see how much range of time did they scan, which that number I don't have in mind. Compared to the child time versus the GW search window is something I don't have in mind. But probably it will include at least post-merger and at the time of merger, because pre-merger may be a little too difficult actually with this GW instruments.
Rashmi, then next slide where you were showing the GW.
Okay. Which one?
It could be said as a precursor to both. Is there anything that you could say here?
No, sorry.
Which one?
Happened first. So BNS merger is first, then 2.5 hours later, the FRB. So this will be something like a post-merger. This will be a post-merger, actually. But this was, I think, the work of Mohit Bharadwaj. I mean, they're really questioning whether there could be any association.
Okay, thank you.